All right, so that's DNSSEC. There are some issues with it. It's not perfect. The primary issue today is deployment. Deployment is a challenge. It's hard to get everyone to move from DNS to DNSSEC. And even today, some domains are using DNSSEC, but many are not. So DNSSEC is not 100% used. And that's a real challenge because suppose .com is not signing, but Google.com is, then we're hosed. We don't have a trust chain that lets us verify Google.com's public key. So we have to get all of the top level domains to deploy DNS. Fortunately, we've gotten that. A more current concern is today .com is signing and Google.com is signing. So they're using DNSSEC and signing all their records. But suppose that CNN.com, for instance, hasn't deployed DNSSEC because they figure, I don't care about security that much. I'm not going to spend the money to deploy DNSSEC. Now what resolvers do? The problem is some queries that they make will come back with signatures. Like when they query Google, they'll get a signature. But when they query CNN, they'll come back with no signature. And that leaves the resolver in a really tough spot. The resolver can either accept unsigned responses, but if they do, that's insecure because a man in the middle could wait for the resolver to query Google.com, throw away the signed response from Google.com and replace it with an unsigned response. And if the resolver is willing to accept unsigned responses, then bam, the resolver is vulnerable for all domains, even for Google, even though Google has deployed DNSSEC. On the other hand, if the resolver rejects unsigned requests, that'd be secure, but then attempts to do DNS queries for CNN.com would fail. And so if you tried to visit CNN.com in your browser, you wouldn't be able to because the resolver would have blocked the response as unsigned and insecure and can't be trusted, and so therefore ignore it. So it's kind of a caught between a rock and a hard place for resolvers right now. If you don't trust unsigned responses, then everything breaks. So that's not really feasible. So resolvers are forced to trust unsigned responses, but then that weakens security and it also weakens the incentive to upgrade. If you think about some new site like, I don't know, Berkeley is considering whether to deploy DNSSEC, and someone points out, hey, Berkeley, even if you implement DNSSEC, clients aren't going to benefit. Clients can still be attacked because they'll still accept unsigned responses. And so a signed response from Berkeley, a man in the middle could still replace with a bogus unsigned response, and resolvers would still accept it. So then from Berkeley's perspective, it's like, oh, what's the benefit to me, Berkeley? It's pretty slender. So this is a real headache. And it's often a headache in deploying networking technology or security technology is getting people to deploy, and what are the incentives for everyone to deploy? So there are some partial mitigations for this, but it's something that really holds us back. Okay, next challenge is how to handle negative results, no such host name. And we talked about an official way to handle that, and DNSSEC does implement that, though it does have the slight downside that enables enumeration of domain names, which most places probably don't care about, but some of them, it's a disincentive for them to implement DNSSEC. Like Apple, let's say that they were going to create a new host name for every secret project they had, and then they create a host name, you know, iPhone version 17, this time the headphone jack returns, .apple.com. Well, now DNSSEC reveals the existence of that host name, and maybe it's a leak that they might not want. So that's sort of downside. Anytime you have a disincentive for people to adopt a security technology, that's not ideal. Okay, and another practical issue is that with DNSSEC, responses are really large because they include a signature. So now the response gets much bigger, like it can be 1,000 bytes or more. And okay, that's probably tolerable. One downside is that it enables denial of service attacks. So we'll talk more about denial of service later, but you can imagine If there's a way that I could send a short query to a DNS server and has to respond with a large response, then there's a way for me to do denial of service. I send a lot of short queries and it has to send a lot of long responses, do a lot of work to respond, and maybe it'll overload its network capacity, or it can create other problems. Okay, so DNSSEC is adopted, but nowhere near 100%. And there's some challenges with convincing people to adopt DNSSEC. But I think it's a really clever, neat idea. And I wanted to highlight for you this distinction between channel security, where we're encrypting a communication, like encrypting a connection. And we'll see more about this when we discuss TLS later, versus object security, like DNSSEC, where the goal is not so much to protect data in transit, but we want to protect data at rest. We want to protect a record in a database or a record in DNS. So now we want our data to have integrity that can be verified. And the great thing about this kind of DNSSEC style security, object security solution, where the data records are signed, is that they can be friendly to caching. Because data is self-authenticating, I no longer need to get data from the trusted server. I can have the data be served up by a replica or by a resolver or by a cache, and I can still trust the data even though it came from some random source who happened to set up a mirror or cache for me. Okay, so the takeaways from this lecture that I want you to take away are, first, to learn about channel security versus object security and when you should choose channel security versus object security, how to use cryptographic signatures to provide object security when you have data records that you want to authenticate, and also to say something about the organization of PKI. Notice how the structure of signatures in DNSSEC reflects the existing hierarchy of DNS names. The root signs keys for .com and .org and .gov, and .com signs keys for google.com and cnn.com. That follows the existing delegation hierarchy and authority structure we have. And so that's a great heuristic you can use if you need to set up a public key infrastructure where you have trusted servers that are signing certificates. What's the structure of that tree structure? Follow any existing hierarchy you already have, and that increases the chances that it'll work well.